Welcome to, let's say, the first official session of science, physics and chemistry, chemistry and physics for grade 10. What I'm going to start with is some of the basic units that we're going to be working with in chemistry and in physics. Okay, we're going to look at things like mass, forces, pressures, changing the subject of formulas, just a few little things, bits and pieces, just to get started with the process. Okay, right. First of all, let's take mass. Right now, we all know. Let me just get the color back. We all know. Let's have a look first of all, and let's start with mass. Okay, the mass of something. When we talk about it, we talk about very often we talk about weight. Okay. His or her weight, or the weight of that is whatever it is. And we look at a pocket of cement, I think is generally something that we know, or a pack of sugar, all right? We say a pack of sugar in a kilo, 2.5 kilos, 5 kilos, 10 kilo bags, possibly even bigger, right? And then we tend to say that that's the weight of something, right? That's not the case. The mass is measured in kilograms, right? So the mass is actually the kilograms, okay? All right? Kilograms. This is basically the unit we're going to be targeting, okay? The kilograms is where we're going to revert everything to. We're going to work in kilograms, meters, and seconds in most of our physics work, and a lot of the chemistry we're going to be working kilograms, but we're going to change that to grams, liters, deciliters, cubic decimeters, and things like that. All right. But first of all, we've got a mass, which is kilogram. Right. So if that's the mass, right, let us say we've got a mass of 50 kilograms. Right. What is then the weight? The weight of that. The weight is defined as the mass times the acceleration due to gravity. And that figure there is A, or let's call it G in this case, which is 9.8 meters per second squared. Right? So the weight of something is the mass times G, which is 9.8 meters per second. It's the acceleration due to gravity. Essentially, if we stand at the top of a bridge and drop something off, it's going to go faster and faster and faster. It's being accelerated because gravity pulls everything in. That's the whole apple concept that Newton asked why this is going to happen, right? So gravity is something that is pulling us down. That's the acceleration. So the weight, as opposed to the mass is kilograms. The weight is basically the mass times the acceleration. And that's measured in newtons. All right? It's measured in a newton after Sir Isaac Newton. All right? So that is the weight of something. Well, technically that's also the force with which is pulling on you. What is a force? Here's my apple over here. What is a force? A force is a push, okay? A pull, like that. A push and a pull. A lift up or a pull down, right? Or we can, something like this, for example. We can be pulling up and this way at the same time, because if you've ever done that, part of your pull is going up and part of it is going horizontal, isn't it? So our force is either a push, a pull, a lift, or a downward pull, which is measured also in newtons, is an element of force. Okay? That's what we're measuring. Our pushes and pulls. Force is pulling us up, a force is pulling us down, a force is pulling us this way or that way, or yes, forces could be at an angle, being pulled up like this, and that way, and other ways. We'll do that when we get to vectors and scalars in physics. But our force is something that's acting on us. When you go around a corner in a car, you've noticed that you are pushed to the one side. There's a force acting on you. Those are the centrifugal and centripetal forces that are acting on a body going around a corner. And when we talk about a body, by the way, we don't necessarily mean a human body, we mean something. For physics purposes, that's a body. It's just something that experiences a force, okay? Let's have a look at another one, okay? Simple one in this case, all right? Pressure. Pressure, all right? Something is under pressure, okay? The pressure is, okay? How do we measure pressure? What actually is it? Well, pressure, let's just think. If I put a force downwards of F, and I do the same thing F there, and I am going to stand on your toe. We'll ask a lady to do this, right? She can stand on your foot wearing, over here, a pair of flat shoes, right? The next thing, she can wear a pair of high heels or stiletto shoes, right? You can see very well, just think about it. You know that if somebody stands like that on you, it's not as bad as if it happens like that. The pressure is greater. Pressure is defined as force divided by area. And force is in newtons, area is in square meters. So can you see here, the P is going to be very high. And here, P is low, right? And now we're not talking about high and low pressure in geographical terms, that's a different thing, although the measurement is the same, the way it's measured. The force over the area, right? So once again, it makes us realize that if this is our item and we're pushing down on it, underneath we're feeling this force divided by the area, and if we make it smaller, like this, the same force is going to actually hurt you because the pressure has been increased, okay? Now what do we measure pressure in? It's got its own units. Yes, it is newtons per square meter, but it's actually measured in something called a Pascal, right? So 1 Newton per square meter is 1 Pascal. Normally pressures are measured in terms of kPa, kilopascal, which is times 10 to the 3, or thousands, or megapascal, which is times 10 to the 6, which is usually these are strengths of concrete and things like that, megapascals and things like that. Kilopascals usually in, or hectopascals very often, is air pressures and things like that, okay? So what we're doing is we're measuring these units of pressure in Pascal, okay? Unfortunately, we've got to go through all of these little bits and pieces. Let's have a look at the next one. Okay, we all know that there was a thing in mathematics which was called literal equations, all right? Just get another page here, okay? Whoops. Okay, I've just added, there we go. Come on, come on. There we go. Right. What I've done is, the next bit is, in maths we did literal equations. The literal equations was called, it was actually changing the subject of a formula, right? Changing the subject of a formula was a literal equation. Why do we do this? Well, let's just take, for example, we have a formula here called S equals ut plus a half at squared. Okay? That's one of Newton's equations of motion, not in the format that you're going to see it. That's in the format that you'd see it if you're doing physics at uni. All right? Just move my Newton apple there. Now, in physics, right, and in chemistry to a slightly lesser degree, but in evidence it's there. what we do is we always put down what we're given and look at what is missing and calculate the rest. So essentially, they might give us this one. They might give us U and T and ask us to work out A. What do? We put in S might be 1,000, okay? U might be 10, T might be 15, okay? Plus a half times A times 15 squared. Can you see I've just substituted in? I've said S was 1,000. I haven't put units in here, okay? Don't worry about that at the moment. It's just this concept we're going through. Is 1,000. U, I said, was 10. T was equal to 15. And now we say that therefore 1,000 is equal to 150 plus a half times 15 squared. I'll have to do it on the trusty calculator. 15x squared equals that, divided by 2 is equal to 225 over 2 is 112.5a. Now we have to change the subject of the formula. The 150 goes across, so we've got 1,000 minus 150 is equal to 1112.5a. Therefore, the next thing we're going to divide both sides by 112.5, 112.5, and that cancels, and therefore we get A equal to, let's have a look, 1,000 minus 150, 1,000 minus 150 equals that, divided by 112.5 is equal to 68 over 9, which is 7.56. Okay, so when we have to change the subject, I prefer that instead of messing around with the equation and going through the process of saying, well, A is S minus that times 2 divided by T squared, I personally prefer to just put everything in, because it shows me, it highlights for me over here that that's what I'm looking for. That's what I don't know. That's what I don't know. It makes it actually simpler. There's less margin for error, because when this is all in terms of, and if you look here, you'll see that this is all in terms of, these are all numbers now, aren't they? There and there and there. It makes it easier to do the transfer across to the other side and do the division. Whereas if you try and rearrange and then put in, there's usually an error that can creep in there. I just think it's more logical to do it that way. Obviously, it's whichever suits you best. Some people like to rearrange and then plug in. I prefer it the other way around. Okay? Now, that's changing the subject of the formula. Right? So always just stick it in and then look at the variable that you want, because essentially all of this work we're going to be doing is just about putting down the state 1 and finding out what's missing in part 2 as it changes, right? Let us look at something about proportionality, because that's something else that seems to get a little bit sort of whatever, okay? Remember, if I'm not sure if you do, but let's just recap it. If I've got a graph that looks like that, it's a straight line graph, right? Can you see here that as x increases, y increases? In other words, they are directly proportional. Directly proportional to each other. If the one goes up, the other one goes up, means direct proportion. Okay? Always look at it and say, if this goes up, what's happening to the other one? Okay? The difference is going to be if we look at a graph like this. Okay? Can you see here y and x? Okay? As y gets bigger, okay, in this case, x gets smaller. So as y goes up, x is actually going down. As x gets larger, y goes down, which means these are inversely proportional to each other. Okay? The one is going up, the other one is going down. They are inversely proportional to each other. Okay? Generally, the shape of the graph looks like that. Right? The other bit, okay, that one is that was temperature. Okay, let's look at exactly here's an experiment that we do, all right? Over here, we measure pressure, okay? Remember, we measure pressure in pascals, in this case, kilopascal. Up here, we measure temperature in degrees centigrade. Let's just call it that for the moment, all right? Actually, we should measure that in Kelvin, but we'll get to him a little bit later, all right? What happens? Think of it like this. We are raising the temperature of something confined in this box. Let's say it's a pressure cooker. You put everything inside it and then put it on a stove. What happens? The heat comes in from underneath. It raises the temperature inside here. There's water in there, inside your pressure cooker, always. What happens to that water? It starts to boil. As it boils, so the pressure inside starts to increase, because that gas has got nowhere to go. It's stuck inside there, right? So as it gets hotter and hotter, the temperature goes up and the pressure goes up. So if the temperature is going up and the pressure is going up, we say that we've got that situation like that, right? Temperature is directly proportional to pressure. Okay, makes sense? All of these are actually fairly logical. Let's look at the next one. Over here, got one here. Pressure and volume, okay? Okay, let's look at this one. And I've got it over here, volume in cubic meters, all right, and pressure again in Pascal, all right? Now let's think about this, okay? Let me put these two boxes together that we've got over here, all right? Let's pretend or think of it in terms of a bicycle pump. When the pump is out, the volume is this size, right? As you push it in, the volume is going down. What happens to the pressure? It goes up. So as the volume is getting smaller, the pressure is going up. We get a parabola, a hyperbola. Hyperbolic shape over there, okay? A lot of you may not have done that yet, it's coming. But you get a very distinctive shape. But logically, all we're thinking about here is take a syringe. I'm sure every single one of you has had water fights with those squeegee guns or a syringe. But take a syringe, a nice big fat one that you can buy, right? What happens as the plunger is out, as you push it in, if you close this end, right, you can feel on your thumb that it takes more and more force to push, because you're compressing it inside. You're increasing the pressure. But the volume is getting smaller, isn't it? That plunger is going in and squishing up all the air molecules inside there. That is a situation of inversely proportional, right? Where are we going to use this? All right. Essentially, we're going to use it in a number of places. This one here, we've got force. Don't worry about all of these symbols and things I'm using. I'm just showing you that the force between two charged bodies, Q1 and Q2, okay? This is Coulomb's law. We're going to be getting to him in physics. The force between two bodies that are charged up, okay? If I push them together, the force is proportional to the amount of charge on this and the amount of charge on this. The more, the greater the force, either to push them together or the greater the force of attraction. But force is also proportional to 1 over the distance they are apart squared. Right? So that means we've got force is equal to, or rather proportional to Q1 times Q2 over R squared. What does it mean? Because F and F are the same, it's proportional to the product of the two charges. In other words, how much they are. And it's inversely proportional to how far away they are, right? If you take two magnets, here's two, right? And you put them together, I don't know if you can see it on my desk, but if we put them together like that, all right, they're far apart. there's very little magnetic force between. As I move, see, they attract each other. Essentially, that's what this force is that we're talking about, right? Now I can say that that's proportional to that whole thing over there, right? What does that mean? Well, it means now we've got that situation there of proportional. The next step is we don't want proportional, so we introduce what is called a constant of proportionality. F equals K, this is our constant of proportionality, times Q1 times Q2 over R squared. This K here lets us remove that proportionality sign and make it equal. All right? I know for many of you this is probably very, very straightforward, but do you know what? A little bit of revision of some of these basics will help quite a lot into the future as we move through these. Okay? So that's some of the, before we now start moving along, that is some of the basic, the core elements of it. The forces, the weights, the masses, pressure, forces, things like that, right? Those are the things we need to deal with. Okay? In the next one, we're going to start with matter and materials, right? So we're actually going to start the chemistry side. We've done some of the revision on conversions, etc. We're going to get stuck into chemistry. We're going to talk about mixtures, pure elements and such, and we're going to take it further. It's quite a lot of theory that has to be gone through, not a lot of calculations. So most of it's going to be talking and looking at some kinds of examples, okay, as we go through. We're going to mix up stuff and talk about things like that, okay? So please bring a notepad into the next one and we'll go through, bring your textbook, we'll go through it together. Thanks for watching this one, and I hope to see you shortly again in the next one.